it can be formulated as follows. Every triangle with angles alpha, beta, and gamma, and the sum of angles alpha plus beta plus gamma is equal to pi. So this is a fifth axiom of Euclidean geometry. But since it is independent from four first axioms, we can replace it, for example, by this. Sounds as follows: that every triangle has the sum of angles more than pi. So if we replace the fifth axiom by this, what we get is a non-contradictional system of axioms and defining the spherical geometry of a sphere. But if we replace the fifth axiom by the following, then what we get is a hyperbolic geometry. So the sum of angles of any triangle is less than pi. Of course, for all three cases, numbers alpha, beta, and gamma are real, and each of them, any of them, are less than pi and order 0. In Euclidean geometry, a triangle doesn't determine geometry by the set of its angles. We need some linear measurement also. But in spherical and hyperbolic case, it actually is. So the spherical or hyperbolic triangle is determined geometry by the set of its angles. And for example, we have nice formulas for the areas of spherical and hyperbolic triangles. So in spherical case, the area is equal to alpha plus beta plus gamma minus pi, and in hyperbolic case, the area is equal to pi minus alpha minus beta minus gamma. So I hope this is enough for us. Calculating then, of course, these examples are just two-dimensional, but of course the axioms works in any dimension. Calculating volumes of Polyhedra is a very old problem. It is well known since Euclid and remains relevant nowadays. Why it is still interesting? The main reason maybe is that the volume of fundamental polyhedron is the main geometrical invariant of three-dimensional manifold. What I mean? Any three-dimensional manifold can be represented as by its fundamental polyhedron. That means we can pairwise identify the fixes of some polyhedron to obtain a three-manifold. Let me show you briefly one example of this kind of construction. So here we started with a cube and we divide every phase by into parts. So actually, the starting polyhedron is a bit more complicated than cube. And then we pairwise identify the traces as shown on this slide. And what we get on the final step is for again rings, we get it into a three-dimensional sphere. And this kind of construction can be done for every three-dimensional manifold. And of course, the volume of three-dimensional manifold on the final step is equal to the volume of prescribed polyhedron on the first step. So this example shows that the volume of three manifold or the volume of node or link and the volume of polyhedron is the same object. The same object. So let me continue. And of course, geometrical invariants are stronger than topological ones, but since most of the utilities here, the geometrical invariant is also a topological invariant. So that is the reason why the problem of volume calculating for Polyhedra is an important problem in theory of three-dimensional manifolds. So I think I should skip this derivation. Here I just outline. In Euclidean space, there is a classification of all three manifolds. In spherical case, there is also a complete list of spherical manifolds. In hyperbolic, the problem is open. You can just arrange the manifolds by increasing of its volume or increasing of the complexity or something else. But of course, there are still manifolds, different manifolds with the same volumes. And that is the reason why we need to know the exact formulas for the volume of three manifolds. And in spherical case, we also need to know the exact formulas, and one of the reasons is the rational volume conjecture. So now let me switch to the main example, which I want to present. So in Euclidean space, we know almost everything about the volumes of polyhedrons. In spherical and hyperbolic cases, the situation is much more complicated. Just a few partial results were known since Lomachevsky by Shletli, and most of results, I mean exact volume formulas, were given last 20 years, many of them. And I have no time to list them. The most interesting, in my opinion, result in this direction belongs to Sforza, Italian mathematician who found the volume of hyperbolic of compact hyperbolic tetrahedron of general type, and this formula is shown on this slide. So you remember that in hyperbolic and spherical spaces, triangle is is defined absolutely by the set of its plane angles. The same for polyhedra. Any spherical or hyperbolic polyhedron is defined absolutely by the set of its diagonal angles. So, if we consider a hyperbolic tetrahedron with 6 given by its diagonal angles A, B, C, D, E, C, and F. We can construct a so-called ground matrix, or we know this board, which consists of minus cosines of its diagonal angles. And so this matrix is symmetric one. Oh, let me use another notation. So we enumerate the vertices, and the ground matrix G is just a matrix consisted of minus cosines of diagonal angles theta sub ij, where theta ij is the diagonal angle along the edge which is connect vertices with number I to vertex with number j. For example, here will be theta sub 1, 2, theta sub 1, 4, etc. So, any hyperbolic tetrahedron is defined by its ground matrix. So all the information about this tetrahedron contains here. But the problem is how to get information from this matrix. We imagine that the first trick that we imagine that this tetrahedron is varying in such a way that 5 of its angles, B, C, D, E, and F, are fixed. But one diagonal angle, for example, A, is varying in continuous and even differential one. Since that, we can consider the ground matrix as a matrix function in terms of one variable, A. And what is C sub 3,4 here? That is a 3,4 cofactor of ground matrix. And here, the integration limits the lower integration. Oh, sorry. The lower integration limit is just the root of the integrand. If you will say that is the root of this ground matrix functions in terms of one variable A. And the upper limit is the given number A, the value of the first diagonal angle. So since this is a cofactor, of ground matrix, which is a function of variable A, then C sub 3,4 is also a function in terms of variable A. So we will integrate it. But how to prove this formula? Sforza published 2 papers, one in 1906 and the second 1 year later, and his proof of this formula was very complicated, more than 40 pages. And also he used some other notation, but it's not important. Together with Sasha and Ednik, we propose a new simple proof for this formula. So, since all the information about geometrical parameters of the tetrahedron are sitting inside this matrix, what we need to get the information from here, and we were lucky to find the convenient relation between matrix readouts, that is a so-called Jakob relation. It relates the determinant of matrix of 4 factors for any squared matrix with the determinant of this squared matrix and the determinant of the corresponding minimum of this matrix. So, just 2 minutes more. So we applied the Jacobi relation for gram matrix of hyperbolic tetrahedron, since that the n is just 4, and we applied it for case when k is equal to 2. In this case, what we get from Jacobi relation is this equation. After that, we combine this equation with the cosine law, cosine rule for hyperbolic triangle. By the way, Sforza didn't know the cosine rule for hyperbolic tetrahedron, and that was maybe one of the reasons why he cannot find a simple root. So we combine these 2 equations, and after some calculations and manipulations, what we get is a formula for the edge lengths. Edge lengths corresponded to the diagonal angle A in terms of diagonal angles of the tetrahedron. So, since we imagine that all the diagonal angles despite B, C, D, E, and M are fixed, this is just a function of one variable A. Then we use the Schnetter formula, which relates the volume differential for any hyperbolic polyhedron and the diagonal angle differentials. And here, L sub alpha is just the edge length corresponding to diagonal angle alpha, and the sum here is taken over all the edges of this polyhedron. But since we imagine that only one angle is varying, this formula is essentially simplified. Then we integrate both parts, and what we get is shown here. Then substitute the edge length by this formula, and what we get is possible. And on the last step, we just carefully check the limits of the equation. That's it. So, thank you.